In this video, we're going to prove the Chinese Remainder Theorem. It goes on to say that if you have n positive integers such that they are pairwise relatively prime, that is, if you take any two of those n sub i's, their GCD will be 1. Of course, if they're not the same. Now, if those pair of R positive integers are pairwise relatively prime, then the system of congruence, these are congruences. So let me put congruences. These are, notice what the mods are. The mods were these are pairwise relatively prime numbers. In this case, it has a simultaneous solution. In fact, this solution is unique modulo the product of those R numbers. These are numbers, n1 times n2 up to nr. The proof isn't that bad. Talking about proofs, if you like seeing mathematical proofs all the time, you should definitely subscribe to my channel. Mainly because if you click on any video, it will be a mathematical proof. That's what you're into. This is a channel for you. So we're going to define some variables. Let capital N be defined as n1, n2 up to nr. In case you don't know, that means 3 horizontal lines. Among many other definitions, it means defined to equal. Maybe I shouldn't use that in a proof that's talking about modulo arithmetic would also uses 3 horizontal lines. So how about we say let n be that, and let n sub I be capital N, that is the product of these R numbers, divided by n sub I. That is, you're going to multiply all those R numbers. You'll multiply all those R numbers except one of them. That one. When you put a hat over a product, let me say that again. When you have a product and you put a hat over one of the factors, that means that factor is not there. So for example, if you had 2 times 7 times 9 times 3 with a hat over it, it just means 2 times 7 times 3. They don't want you to include the 9. Now, of course, in this case, if I didn't want to include the 9, I would just write 2 times 7 times 3. But it's, maybe not talking wise, but it's a lot easier to write this than to write n sub I minus 1, skip n sub I, pick up at n sub I plus 1, and then go to nr. They both mean the same. It's just a little easier. Okay, so that's the definition. And of course, this is for any I equal 1, 2, up to R. That is, n sub I has now been defined for I between 1 and R. Now, since the little n sub i's are all relatively prime, so let's state that. Since the n sub i's are all pairwise relatively prime, because any two of them have a GCD of 1, relatively primes in pairs, like I said, 2 of them, that implies that the GCD of n sub k, capital N sub k, and little n sub k is 1. Because n sub k is n1, n2. This time I'll write it n sub k minus 1 times, not times. I mean, not a list, times. n1 times n2 all the way up to nk minus 1, n sub k minus 1, m sub k plus 1, all the way down to n sub r. And then you have n sub k, which is just n sub k. Now, nothing that goes in here goes into n sub 1, nor does it go into n sub 2, nor does any number that go into here go into n sub k plus 1, all the way to n sub r. Nothing in here goes in there. That's why this is true. Well, I take that back. I always say nothing, but there's always, the nothing really means 1. The only thing that's common in n sub k and n sub 1 is the number 1. N sub k and n sub 2 is the number 1. Okay, nothing goes into them other than 1. Okay, so that was just scratch work to justify their statement that underlining. Okay, now, since that's true, that implies that n sub kx is congruent to 1 mod n sub k. Now, nk, capital NK, and little nk, they are relatively prime. That means there are inverses for n sub k. Like if you had 3x is equal to 1 mod 7. 3 and 7 are relatively prime. There are inverses. That is, I can multiply 3 by something and get 1. What is that going to be? It's going to be 5. 3 times 5 is 15. Take away a couple of 7s, you get 1. Okay, if these two numbers are relatively prime, there's always a solution. In this case, inverses. Okay, now let's state that. Now this has a unique solution. Let's call it x sub k. So nk times x sub k is congruent to 1 mod nk. This equation does have a solution because the inverses exist. Okay. So now, well, let me just say one thing here. And it has a unique solution for all k equal to 1, 2, 3, up to r. That means that n sub 1 x congruent to 1 mod n1 has a solution, n2, and we're calling that solution x1. That is, n1 times x1 really does equal 1 mod n1. And n2 times x2 really is congruent to 1 n2 all the way down to n sub r, x sub r. By definition of x sub r, it's the solution. So n sub r times x sub r is 1 mod n sub r. Okay, so now that we have that, now I'm going to make an amazing claim. I make the claim that x bar, which is equal to n1 x1 plus n2 sub x2 all the way down to n sub r x sub r, n sub r x sub r is a simultaneous solution to our system, of linear congruences. Now, we need to establish a few things. First, observe the following. First, observe that n sub I is congruent to 0 mod n sub j, if I and j are not different. And the reason is this here contains a factor n sub j. So n sub j, little n sub j, divides that. This is since little n sub j divides big N sub j. Now, N sub I, big N sub I, just like I wrote. Big N sub I. I wrote it here. Okay, so now we have that. Now this is for all I not equal to j. Okay. Now let us see if our solution really works. We're claiming that x bar, which is a A1, so let's see one little thing here. Okay, so what we have is A1 times this, A1 times N1 X1 plus A2 times that, N2 X2, etc. N2 X2 all the way down to AK NX or NK x sub k all the way down to a sub r nr times xr. But now, what does this equal? If we're doing this in mod, say, n sub k, mod m sub k. Now, we know that if these subscripts are different, we get 0. Okay? If those subscripts are different, well, this subscript and this subscript are different. That is, that's 0. This subscript 2 and n sub k are different. That's 0. This subscript and this subscript are not this different, so we'll talk about that in a moment. And those two subscripts are 0, are different, so we get 0. So this is congruent to a sub k, n sub k, x sub k, mod n sub k. Now, here's the beauty. That equals 1. Somewhere we said that. Remember, we said this is congruent to 1 mod nk if nxk is the solution. That is, when we put these two together, we get that nk times x sub k is congruent to 1 mod n sub k, because this x right here is unknown. And I'm saying that that's the solution. It has a solution. Let's call it x sub k. So down at the very bottom, that's 1. So what we get is a sub k times 1 mod n sub k, which is, multiplying by 1, is a sub k mod n sub k. Okay, that is, x is equal to this. And that's really what we wanted to show. And this is for all k from 1 to r. Okay, so this x works for each and every mod, no matter what mod we use. That is, now you don't need this in the proof, but x bar is congruent to, now I'm just copying this. X bar is a solution to a sub 1 mod n sub 1. X bar is a solution, that is, it is congruent to a2 mod n sub 2, all the way down to x bar is a solution to the congruence of a sub r mod n sub r. So this x, that is the way I defined it up here somewhere. This x, which is equal to this, is the solution to all of those r linear congruences. Okay, so we don't need this. So now I prove that there is a solution. Okay. This shows that there does exist a solution. That a solution to the given system of linear congruences does exist. It exists. I know it is. It's x bar, the way we found it. Now I have to show uniqueness. I have to show that it's unique. Okay, so, like always, let x bar be another simultaneous solution to our system. I'm not going to write that again. Well, then it's obviously so that x bar is congruent to a sub k, which is also congruent to x bar mod n sub k for all k's. Okay. That is, x bar and x prime is mod nk. Well, let me not say that. X bar and x prime are congruent to a sub 1 mod n sub 1, and x bar and x prime are congruent to a sub 2 mod n sub 2, all the way down to x bar is congruent to x prime, which is congruent to a sub r mod n sub r. Okay, so this last statement says that n sub k, so n sub k divides x minus x bar. I mean, basically, just ignore this for a moment. If this is congruent to that mod n sub k, then m sub k will divide the difference. And this is for all k's. For all k equal to 1, 2, 3, up to r. Now, here's the beauty. Since the GC, now, just want to be clear. N sub 1 divides this. N sub 2 divides this. N sub 3 divides this. All the way down to N sub r divides this. But they have no number in common other than 1. They have no number in common. Both of these statements, this implies that N1, N2, up to NR divide X bar, it should say, X bar minus X prime. But remember, this is another name for N. Well, this implies that X bar is congruent to X prime modulo N, capital N. And that completes the proof for uniqueness. Up to modulo N, there's only one answer. If you come up with another one, it equals to the original one, mod N. In other words, if you had mod, 17, and 19 is congruent to 2 mod 17. It's okay for one answer to be 2 and one to be 19. Because mod 17, they're the same answer. These are basically the same number. Okay, you won't get that X bar is 3 mod 17 and say X prime is 5 mod 17. Okay, because 3 and 5 are not the same in mod 17. Their difference, 17 doesn't divide their difference. 17 does not divide 2. It does not divide it. So they're not, 3 and 5 are not the same mod 17. It would be a problem if what I'm about to raise happened. But no. We picked another one. We said let X prime be another solution. And we concluded that modulo N, they're the same answer. They're the same value. So we prove uniqueness. Let's get rid of this. And there's your proof. Once again, if you like seeing mathematical proofs, please subscribe to my channel. Leave a comment. Hit the like button. See you guys in the next video. Watch and learn.